So very good afternoon, everyone. Uh, in this post-lunch session today, we have Sri Devang Patel with us. He is an veteran bridge engineer, having experience for more than 18 years in designing infrastructure projects, but he is more specialized in bridges. He has altogether designed more than 150 projects of bridges, flyovers, ROBs, pump houses, FOBs, irrigation infrastructure, jetties, etc. Moreover, he is also a seasoned professional in irrigation and water supply, marine structures, steel structures, and hydel projects. Academically, he is associated as a visiting faculty for design of bridge and pre-stressed concrete design with very reputed institute like SEPT as well as Nirma University since last 12 years. Okay. He has guided many projects from both the institute from SEPT as well as Nirma MTech thesis. He has delivered dozens of expert lectures and published research papers in various conferences and journals. Sir is basically a professional, but he is having teacher's heart. So definitely this session is going to be very much uh, understandable for all the participants. You will love to hear from Devang sir. So with this, I request Devang sir to take over the charge and continue with the session. Sir, please.
Yes, sir. Thank you.
Yes.
I think my presentation is shared properly.
Yes, sir. Yes, sir. It is visible.
Right. Okay. Right. So, good afternoon, all. Today, we will discuss about the seismic analysis of the bridge. What practical approach we as a designer adopting along with the current science and the quarter provisions of the bridges. Just to get into the subject, I generally prefer to start with a starter, right, so that we can be involved from surrounding environment into the subject. So, to give the emphasis on the bridge, what is the bridge as a structure in a philosophical way? It is that structure. If you stand in between of any of these structures, you will feel very relaxed and find that there is nothing is surrounding, and you can have a very peace of mind. In the way of the seismic context, we can say that it's basically a human nature, and it very well reflect to our structures also. The more we remain rigid, we have to sustain very high stresses and have to face many problems and difficulties, and sometimes we may break down or shake down sometimes. And the same philosophy is applicable to the bridge also. Not only bridge, to all the structures. Rigid structures generally attracts more stress, more stresses, and vulnerable to more failure. Right. So basically, try to remain flexible, determined, and just follow the rhythm of the structure, rhythm of the nature, and just apply the similar rule to our structure also. Propose our structure so that it have the more flexibility, determinacy, and everyone can understand easily the form of the structure. Basically, with every earthquake, uh, if we see the history of the past earthquake, it has just not break the records. It means some 4 Richter scale earthquake the next year in the some other region, it is 5 Richter scale, somewhere 6, 7, 8. So it's not just record in terms of the intensity, but it has also breaks the rules. When we talk about the breaking the rules by the earthquake, it has been observed that entirely each earthquake has changed the philosophy, engineering and science, what we have applied in the design and analysis of the various structures. So every time we come to the new things, new theory and new aspects. And this is how our whole earthquake philosophy, all earthquake codes has been developed. It is not basic on the just basic engineering or basic rules. It is from the observations of the past earthquakes. Uh, when we say failure, so failure is not just only the step down or go behind the progress. Always the important aspect of the failure is that it is a learning experience. Right? In any failure, if you observe very minutely the failure, we can learn a lot. Rather, there might be a very small things which we can learn from the success, but there are the many things, many aspects which we can learn from the failure. Right? And all the recent sophisticated codes all over the world for the seismic design has been developed based on the failure analysis, failure observations, study of the structures which are failed during the past earthquake only. Now, as we are going to discuss today for the earthquake analysis of the bridge, I just want to give you some little brief about the structure of the bridge, because I'm not sure that how much everyone is conversant with the bridge geometry and its formation. And to understand any structure's behavior regarding any force action, it is most important to understand its formation of the structure, its geometry itself. Right? So uh, basically, a bridge is made up of three components. The topmost component, which is uh, the highest elevation in the bridge, uh, that is called the superstructures. Right? The part below the superstructure is called the substructures. Right? Basically, substructure provides the platform to raise the superstructures, and the bottommost part is the foundation. Basically, foundation is for the purpose of very similar to the other structure, to transfer all the forces of the superstructure and substructure to the firm ground, so that the entire structure can withstand and flow the entire force to the foundations. Now, this is just what how the bridge is composed. Uh, there are bit difference between the building and bridge in a way that building is basically made up of three components, main components, that is slab, beam and column. And all these three components are internally connected with each other. Right? It forms altogether a frame structure. But it is not like in the bridge. Uh, Bridge are having simply supported structure type of the system most of the time. When we say simply supported, it means the entire superstructure is directly resting on the pier only. Right? So it means it is not connected with the pier. It is supported on the pier. The superstructure rests on the bearings, which transfer the force to the pier and foundations. Right? Uh, if we talk about what are the type of the superstructures, so basically there are three types of the superstructure is there. One is the slab bridges. Slab bridges are very similar to the slab of our buildings, but comparatively having higher thickness, more width, because it has to withstand the higher vehicular loading. Second type of the superstructure is the eye girder bridges. Eye girder is basically a long beams having the larger depth than compared to the building beams. Right? But several beams are put together to form a superstructures. And the third type is the box girders. Basically, box girder is the reformed shape of the eye girder only. All the eye girders are connected with the slab at bottom also. Then we can found a box girder, which is hollow inside. This is basically three basic and widely used shape of the superstructure. There are also others also, but with these three all we can discuss very easily the seismic analysis. So as we discussed over here, it is a simply supported span, right? So superstructure is supported on bearing and bearing is supported with on the pier. It means superstructure is not directly connected with the superstructure. Pier. Now another form of the superstructure is the continuous span. If you see in the previous slide, there is a gap between two span. Right? If you see over here, there is a gap between two span. Right? That is basically to allow the superstructures to contract and expand under the thermal variations, right? So that the internal stresses due to the temperature variation do not affect the structure itself. To release those stresses, the gap is given, and in another form, the gap is not there. So two span are made continuous. This gap is not over here, right? And we can have a continuous superstructure. Basically, most of the time it is very similar. Most of the time it is very similar to the simply supported structure itself. But because the adjacent span is interconnected, the benefit is that if we are having a curvature in the plan, the stability of the structure is more confident in continuous type of the structures, because the load shared by the one span can be transferred to the other to keep it in a stable position. Now, third type of the superstructure arrangement is the integral bridge. Right? In integral bridge, there is basically no bearing. We can say it is more or less like a building structure. Pier are directly connected with the substructures. Right? So concrete and reinforcement of the pier and superstructure are interconnected with us. In this case, we have to consider this is a monolithic structure, or we can consider the frame action of the entire bridge system. Now, from these three types of the superstructure, we can understand that the force transfer mechanism from superstructure to substructure is in a two-way. If it is a bearing bridge, the force is transferred to the bearing. Okay? And if we look to this system from seismic context, basically this is a flexible system. Superstructure do not attract any react to any seismic force. It just acts as a lump mass. Okay? Under the action of the seismic, the superstructure will not generate any stresses internally. It will just act as a lump mass, and whatever the seismic effect is, it will transfer to the substructure through bearings. As it has no capacity to sustain or develop the stresses under seismic, it allows a displacement because it is just simply rested on the bearing. So the deficiency of this type of the system is that there is a danger of fall of the superstructure under the seismic condition due to the horizontal force acting on the superstructure. In integral, it is monolithical. So the dislodgement of the span or collapse of the span of the superstructure is not there. So this is the benefit over here. Okay. But now this is a stiff structure. In the first through bearing structure, the piers are pure cantilever. It is just taking the load from the lump mass. So those are more flexible. But now this structure in the integral bridge, it is more stiff. No longer determinant, it is indeterminate structures. So there is the possibility that the stresses from one member to another member can disperse very easily. So seismically, these two characteristics is very important, that superstructure will not collapse under the seismic, and the stresses from one member to another member can be transferred. Now, this is what we have discussed about the type and formation of the superstructure. Now, just we'll look at the type of the pier. Basically, pier is a column. What we are seeing in the building, that is a column. The similar element member is over here, the pier. But compared to the building's columns, basically pier are more in the size, because the spacing of the pier is quite wide, quite long compared to the building. Generally starting from 10 meter to 50, 20, 15, 20, 35, 40 meters sometimes. So it has to have the higher sizes. First type of the pier is a single column type pier, which may be a shape, maybe circular, square, or rectangular. Second type is a wall type pier. Basically, it is very similar to the rectangular pier, but when the larger dimension of the column is 4 times more than the small dimension, then it is called as a wall type. So it means to say that now it is not more rectangular behavior, it will give as a wall type behavior rather than having a column behavior. So second type is a wall type. Many a time we require to support a very wide structures, very wide superstructures, and we require the very wide column base. In that time, transverse frame type systems we can follow, which is made of the various several column structures framed together with a beam at top, beam at below the bearing. So basically, three types of the columns we are using in the bridge structures. Now to just have the quick summary regarding the bridge and building geometry. Difference between the bridge and building is the main characteristic is that of the indeterminacy. Right? Basically, compared to the building, um, bridge is more determinant. Right? If we say that superstructure is more or less, it is a simply supported, and pier is a pure cantilever. Right? So, because of this reduced indeterminacy of the bridge, uh, structure has very reduced potential of the energy dissipation and load reduction. Now, energy dissipation and load reduction is those characteristics of the structures which is highly required in the event of the seismic. But fundamentally, when we propose a simply supported structure supported on the bearing, these two characteristics is highly reduced. A second difference is that in the building, the entire uh, structure of the building is act as a complete frame, right? But here the superstructure, which is a topmost structure, is just act as a mass. So you just imagine that there is a one cantilever support is there, and at the top of the cantilever, one lump mass is put. So it will produce the very high amount of the seismic force to the foundations. Right here, unlike the building, the slab put over the pier will not give the diaphragm action. It will just act as a mass only and contribute to the seismic weight itself. Now, basically, we just want to understand that how we analyze the bridges under the seismic. So, just we will start in a way that how the engineering and science of the seismic design of the bridge has been started. So, just we first try to understand how the bridges were affected or damaged during the seismic, so that we can summarize that what are the vulnerable area or what are the critical points that we should consider during the design of the seismic design of the bridge. Um, the most vulnerable and most dominant failure we have observed during past earthquakes, and most of the time, is the flexural failure. Basically, in the flexural failure, the element which experience the highest flexural stresses fell first. Okay? And in bridge, the highest flexural stresses are observed in the pier because it is a cantilever pier supported at base it only, and it attracts the highest moment at the base. Okay? So if you see in the photograph over the slide over here, you will see number of series of the piers are failed during the earthquake at the base itself. So this is a failure flexural. Second is a shear failure. Right? Sometimes the uh, ultimate limit of the flexural stresses are not reached, but prior to that, the shear stresses are crossing the limit, and we feel the shear failure. And I think you must be aware that shear failure is always a brittle failure, right? And in our structure, we generally do not attempt to have any brittle failure, right? Because it is sudden, without warning, and lead to the complete collapse of the structure. We do not give any warming process. So flexural failure, and this is the shear failure. Third one is the superstructure dislodgement. As we have discussed that superstructure in bridge is not connected with the substructures. It's just put on it. And during the seismic action under the horizontal forces, entire superstructures may dislodge from the substructure. So it can be observed that the structure is not damaged because of the earthquake forces itself, but it is damaged because structure has dislodged from its position and fall down from the several heights. And because of this falling down from the height, it is distressed or it is damaged or it is collapsed. So in the bridge, if you see the history of the failure of the bridges during the earthquake, the more number and more fatal failure we have observed is due to the superstructure dislodgement. Uh, if structure is not entirely dislodged from the support, it might then have the displacement, as we see in the figure at top. Uh, it is slightly dislodged from its position and the corner concrete are crushed due to excessive compressive stress. In this case, it is not a failure, but we cannot use this structure again after earthquake before carrying out the proper repairing and rehabilitations. Fourth and last one is the foundation and soil failure. This is the most vulnerable failure. Uh, Very difficult to predict, very difficult to engineer, and at the same time, it is very difficult to find out the proper solution for that. Basically, what is happening that if our soil is prone to the liquefaction characteristics, so during the seismic, when the soil mass around our foundations are prone to the liquefaction, it just loads its all capacity to withstand the force. I think you must be aware of the liquefaction. Basically, liquefaction is the uh, losing the shear capacity of the soil, right? And once the shear capacity of soil is lost, it is more or like as a fluid. It is not now a confined or solid mass, and it cannot have any bearing capacity to withstand the forces of the structures. Okay? So this is the most vulnerable, and once this failure is occurred, it is, we can say, it is next to impossible to repair the structure. We entirely have to discard these structures because the foundation's failure, it has a greater depth, it is not open. We cannot open entire foundation and we cannot understand what is the extension of the damage occurred below the ground. So this is the very critical to be taken care during the seismic analysis of the bridge. And most of the time we have observed in the practice that geotechnical report which we are using in our design is merely we use to just understand, to take up the single value of the SPC or pile capacity, that's it. We never look into the bore log, never look about the description or recommendations given by the geotechnical engineer and what precautions he might have given to them. Because many a time it is observed that if soil is prone to the liquefaction, it is not like that all the depth of the soil in particular area is prone to liquefaction. There might be possible that at certain depth, certain pocket of the soil, certain depth of the soil is prone to liquefaction. So very clearly geotechnical engineer might have uh, point out in the soil report that you just take care that you are not resting your support or your foundation in this depth of the soil. So in the design, if we overlook this, whatever the highest capacity we are getting, our foundation may fail during the seismic phenomenon due to the liquefaction. Now, if we observe all the cases worldwide for the various seismic, we can find out that most vulnerable or most seen observed failure is the failure of the pier. Right? Because as we discussed that it is getting the highest flexural moment, right? It has the higher stresses to withstand during the seismic. Right? Basically, before failure, the structure itself yield, right? And when during the yielding, surrounding concrete, if we cannot withstand as a single unit intact mass, it causes the failure. Uh, to predict the failure mechanism, we must have to understand the philosophy of the plastic hinge. Right? We'll more discuss detail about the plastic hinge in the subsequent slides, because plastic hinge is that parameter or that behavior of the structure which itself have the capacity to take care of the entire force of the seismic of the structures. Uh, to understand the plastic hinge, we should have the proper understanding of the confinement, shear, yield prediction, yield penetration, and buckling of the bar. Because when we say that some structure has yield or it has lost, overgone his yield limit, it is not just a single sequence or single phenomena. It might have lost the confinement, it might have overstressed because of the shear, it might have opened. It might have uh, happened that all the main force taking reinforcement, vertical reinforcement in case of pier, are buckled out but not failed. Right? So all these four parameters are very important to understand the plastic hinge and failure of the pier. Basically, the insufficient amount of the confinement, it is the root cause of the failure of the structures. Right? Because if proper confinement is not given, yield penetration of the plastic hinge give the extensive damage, and this damage is very sudden, and this damage also can be penetrated to the surrounding member also. The surrounding member, when we say surrounding member in case of the bridge, it is the foundation, and the foundation fails, as we discussed in the earlier slide, there is no way out to retrofit it. Now just we understand that what are the basic principle for the seismic design of the bridge. Right? So what we have understood from the geometry of the bridge is that it is very simple structures. Right? Structurally very determinate. Right? A form, shape, and here is very simple. And but as it is very simple, it is very sensitive. Right? There are very small chances or very small arrangement that the stresses from the one element can be transferred to the other element. Because if there is a chance that the stresses from one element can be transferred to the other element, there are the chance that the locking of the stress cannot be occurred. Right? And if the locking of the stresses are not occurred, it is very easy to withstand the any seismic force to the member. Secondly, structure is not monolithic. So even if we find out the way to make the column or foundation strong, the superstructure is still vulnerable for the collapse from its position. Right? And more critical, the failure in the case of the bridge is because it is told that if bridge fails, system fails. What we mean by that, suppose you just imagine that there is a earthquake in some particular area. Now, in last few years, 4 to 5 years, the practice or understanding philosophy of the all the country was that to increase the capacity demand of the structure so that we can meet the event. It means suppose some magnification of the earthquake force is given today, and tomorrow we experience any more earthquake, we just increase the capacity demand of the structure. Uh, Now, what do we mean by capacity demand? To take a very simple example, Suppose a pier, cantilever pier of particular size and reinforcement is capable to take up of 50 kilonewton of the moment, kilonewton meter of the moment, and we observe last, we can say last 2 to 3 decades, right? But then it is observed that day by day we are just increasing the concrete capacity, concrete sizes, and we are adding the material. But even though we are not reached to the final satisfactory solutions, and we are making our structure more uneconomical, and even though with the next aspect we are getting some damage to it also, right? So now the current international practice is now focused on the performance based design. Now, performance-based design is different from the capacity demand-based design is in a way that just instead of just increasing or just adding the material to the structure, it is the science of the observing that what type of the structure we should propose under particular seismic condition so that it can perform properly. When we say that performance of the structure, then we have to give more emphasis on the structural system, flexibility of the structures, and adequate detailing. Now, adequate detailing is very important, which we'll discuss at the last phase of our presentation. So, while we propose structural system, flexibility, and detailing, basically it does not mean that you add the material, but it means that whatever the available material we are having, you just make the best use of it. And the second philosophy which is introduced along with the performance-based design is that uh, basically we should intend to design the bridge in a way that it should have the proper serviceability during the earthquake. Basically, nobody want to have the earthquake proof, seismic proof design. Basically, we along with this performance-based design, it is observed that we should ask our structure or we should detail our structure in a way that if suppose just damage is to be happen during the earthquake, it should be at a location where we want. When we say that at the location where we want, it means that location should be easily accessible. It should be very easily observable. That yes, during this earthquake, the damage is there. We can magnitude the extent of the damage, and we can easily repair it. Okay? It should not happen, or we should not intend to design a structure there. We are not aware during the designing that from where structure will collapse or where structure will damage. Second important philosophy has been developed in the recent code is that our prime intention should be there that foundation should remain undamaged. Whatever the configuration, whatever the structural size or structural system we propose, we have to take care that foundation should not damage under the occurrence of the earthquake. Now, why code is emphasizing on the foundation should not damage? It is because, first of all, it is the buried structures. Right? After earthquake, one cannot visually inspect that what is the damage over the foundation. Even we cannot predict whether there is a damage or not. Right? And even if we expose the foundation and come to know that there is a damage due to the earthquake, it is very difficult to carry out the repair of the uh, damage of the foundation because it is very confinedly surrounded by the soil. We have to remove all the soils. And after removing the soil and carrying out the remedial measure of the foundation, we have to ensure that the capacity of the soil is still there to withstand the design loads from the superstructures. So primary code is not allowing to design in a way that foundation will be damaged during the seismic. For that, the indirectly code has suggested that the weakest link in our structure should be the pier end, bottom of the pier, because pier is a cantilever pier, right? At the connection of the pile and pier or foundation and pier, it is the zone where it will extract the maximum moment, and it is highly prone to damage during the earthquake. So we should concentrate our design during the seismic at the pier ends. Now, with all this background, we just see that how seismic codes of the bridge has been developed, what was in the earlier and now what we are practicing today, essentially. Uh, Earlier, there was only one code in India for all the type of the structure, that was IS 1893, which was initially published in 1962. Okay. Starting from the 1962, when first time the IS 1893 was published, it was not intended during the publication of this code to lay down the regulations so that structures shall not suffer any damage during the earthquake. Right? It means during the formation of the code itself, it was accepted that even after designing the structure based on this code, during the earthquake, structure will uh, have some damage. Right? But the principle which was emphasized in the implementation of this code is that as far as possible, structure should able to respond to the earthquake with minimum structural damage but without collapse. Right? Now, this without collapse is very important essence of this code. The code is guiding us to design the structure which should not collapse during the earthquake. It is okay if it damage, which damage can be irreparable. Yeah. Now, in 1962 and 66, when the code was initially published, it was the whole country was divided in 5 seismic zones, right? And in the subsequent year, it was revised very frequently, 70, 75, 84. Right? But the revision and the theory of the code was more or less similar. Right? It was after the frequent major earthquake in the different part of the India, like Uttarkashi, Latur, Bhuj earthquake of 2001. Now the code committee has realized that now it is a high time that our code should be completely reformed from its past. Now code has been divided into 5 parts, and each part is dealing with a different type of the structures, right? And part three of IS 1893 is dealing with the bridge and retaining wall. We'll discuss this for this on this also separately. And IS 1893 part 3 is dealing with the bridge and retaining wall. So there is a separate code for the design of the seismic design of the bridge itself. So IS code is basically the code published by the Indian Standards Committee in the field of the bridge engineering. All the regulations and all the codal provisions are established by IRC, that is Indian Road Congress. Number of extensive elaborated codes has been published by IRC in the different category for the different purpose. It is a lot in number. If you can say it is more than 100 or 200 codes are there for each particular component of the page. Right? So it is IRC 6, which is first time introduced in 1958, which is covering the seismic criteria. Basically, IRC 6 is for the loads and stresses to be considered for the design of the bridge. In this code, in 1958, seismic was covered. Now, in this code, when it was published in 1958, they have defined only 3 seismic zones. Right? And also, the seismic zone are not like 1, 2, 3 or 2, 3, 4 like zone number. It was based on the seismic damages. It was categorized like liable to severe damage, liable to moderate damage, and minor or no damage. Right? So, if we compare the IRC6 with the IS code, IS 1893 at that time, itself there is a vast difference of the philosophy and the provisions. But unfortunately, till 1979, this code was not revised. So there was no any further improvement from the seismic point of view. Code again revised in 1981 when the whole country is divided into 5 seismic zones, very comparable to IS 1893. And first time, the horizontal seismic coefficient method was introduced for the seismic design of the bridge. The horizontal coefficient method is purely based on the coefficients. Right? First for the zone factor, second for the importance of the structures, and third is the type of the soil on which our structure is standing. Now, starting from 1981 to 2008, the seismic concept was based on basically this seismic coefficient method only. Widely, we can say that it is a force-based design that users find out the maximum force which structure has to withstand during the storm. But it has very limitations. Very limitations means that if you look at this all 3 coefficients, importance factor, zone factor, and soil factor, there is no consideration of the stiffness of the structure. Whatever type of the structure you propose, the seismic force in particular area will remain same. This is very unlogical. It means that seismic response of the structure is not important to compute the seismic force itself. Okay? But it was in practice for very long duration. In 2008, some improvement has been carried out considering that earlier up to 2008, we have to just design the bridge for the seismic in a one direction at a time. It means if we have to consider seismic in X direction, we have to apply the total seismic force in X direction only. In the second load case, we have to consider in Y direction. So 2 forces or 2 directions are separate, not interconnected. But in 2008, it is imposed that we have to consider the seismic force in the structure in 3 dimensions or 3 directions. Right? When we say 3 dimensions, then it means that 2 plane dimensions, X and Z, and 1 vertical directions. So according to this code, first time it was imposed that when the seismic force is acting in X direction, so we have to design for 100% of the seismic force in X direction, but at the same time, we have to consider 30% of the seismic in right direction and 30% of the direction in Z direction. Okay. So 100-30-30 rule is employed in the 2008. Now this is more systematic because it is very logical that if we consider that seismic force to the structure will act in the single direction, it is not possible because direction is a very global and our structure may be oriented in any of the directions. And it is we cannot ensure that seismic will act in the X direction or particular direction only. Right? So component of the other direction to the seismic has to be taken care, and this was incorporated in code of 2008. At the same time, dynamic earth pressure what introduced that it was considered that during earthquake, soil will also extract additional dynamic pressure to the structure. Hydrodynamic force was also introduced. The water body also will come. Extract or develop the additional dynamic forces. Now, if we compare the various code in implementation in India during 2008, it is observed that there is vast difference, very large difference in the various codes itself. So at this stage, it was very highly required that at least in a single country, the seismic philosophy should be at a single table. It should have the single philosophy. No doubt it might have the different rules because depending on the type of the structures and variety of the structures. But basic philosophy should be at one table itself. But it was not up to 2008. In 2010, now this is the year when the Indian Seismic Code has just started to make up with the all developed countries or try to implement all the new concept of the seismic. And here, seismic coefficient method along with the response reduction factor was introduced. Right? So the coefficient method is now obsolete, is not no more existence, and the equations of the response reduction has to be considered to find out the seismic force. That is Z by 2, I by R, SA by G. Here R is having a very important role, and now it is very logical. Basically, R is the response reduction factor, and R gives the what is the flexibility or what is the behavior of the structure under the seismic. Depending on, we can apply the reduction factor to the structure. It means in a particular area, in the same area, if we are having the different geometry of the structure will have to take the different magnitude of the force. Now this is logical. In seismic coefficient method, whatever type of the structures you are having in a particular area, you will have the same amount of the seismic force. But during this, the major challenge which in field we have faced is that because code was not revised almost for 30 years, right? After Bhuj earthquake, it was a very practical question in our mind that in spite of such a high intensity of the earthquake, if we have not observed very, very, very severe damage in the bridge, which actually we have observed in the Western countries. I'm not sure if you are if you have tried anyone anytime. If you see the history of the collapse of the bridge in the world, you will see that most of the severe collapse has been observed in the foreign countries. It might be a Japan, it may be America, it may be New Zealand or something. But surprisingly, during the Bhuj earthquake, comparatively we have seen very less damage to the bridge compared to the which damage we have observed in the building. Right? This is not because just because of the good provisions of the provisions of the bridge, but there are many other practice also that the codes are very wide. The design codes of the bridge are very elaborated. There is a proof checking agency always involved in the design of the bridge, and proper detailing and guidelines are very clear in the bridge codes. But at that time, the dilemma was there in the mind of the engineer that even if because of the Richter scale of 8 earthquake, magnitude earthquake, if most of the bridges are sustaining the bridges, do we really need to revise our code? Right? When we say that we are revising our code, it means we are having some limitations in our existing code. Right? So even ourselves also were very surprised that there is no problem at all in the bridge. Why should we consider the new philosophy, new design concept, higher seismic zone for the bridges? But later on, as we study all the codes, we keep on practicing on the design philosophy, try to understand the philosophy, we come to know that the intention of code is not just to have the safe structures. Intention of code is many other. It means that we should have the perfect understanding of the science of any force. When we say the science of the any force, and when we also argue the structure has not collapsed, so there may be a very other reasons also because of which structure has not collapsed. So just on the data of the structure's existence, we cannot rely that whatever the theory or whatever the practice we are adopting, that is a foolproof. There should always be room for the betterment. Uh, the other main problem, first problem was that almost 30 years the code was not reviewed, and other problem was that up to 2010, or we can say 12 or 13, the seismic provisions in the Indian code, IRC code, was just covered in 4 pages. At the same time, when Kalstan and Japanese code having the specific seismic code of 200 and plus pages. Right? So you just see the difference. What is the detail we are having while designing or analyzing seismic bridge, and the other countries are having. Right? In the just 4 page, all the aspects which we have to consider in the bridge which are covered. So recently introduced IRC Special Publication 114 has removed all these limitations. Right now, this is a special code for design of the bridge, IRC SP 114, which is extensively, elaborately discussed about the seismic behavior of the bridge only. Right? It is also approaching towards the new analysis techniques, design methods, and now it is very compatible with the other international practices. First and prime importance in the ISP 114 is given that there is a state of art design should be followed while we design the structure. Right? And in this code, most of the chapter, if we read the most of the chapter of this code, we can feel that the code has just tried to fill the gap between state of art and design practice. Nothing new they have given, just they have tried to give the structural system of the prime importance. Right? So when we say about the state of art design, we can differentiate it in 3 main categories. First is good structural configuration. Means we should propose our structure, propose the geometry or structure in a way that the shape, size, and system is directly ensure that there is a smooth flow of the inertia force. Right? And this smooth flow, starting from top of the superstructure to the bottom of the foundation, should be freely transformed from one element to other element. Because when there is a stress flow is locked at one location, it is the highly stressed, and it is more vulnerable for the collapse during or damage during the system. Second is the lateral strength. Uh, very logical that because seismic primary or principally extract the lateral forces, we have to concentrate on the proposing the system that it has the lateral strength. Well, when we say system and the element, it is an entirely different 2 categories. Instead of putting a lateral strong member, we should establish a system itself as a whole that it is a strong lateral. Right? If you want to propose a lateral strong member, then a single member should be very strong, right? And it should consume all of the material itself, the member. But if you propose the good system, with the very tiny and thin member itself, we can have the laterally strong system. Good ductility, right? During the earthquake, it is seen that any structural system which is able to undergo the large deformation, right? Before yielding and even after yielding, it is performing a very good during the system. Right? And the large deformation within the material used is possible because of due to only detailing only. Right? So detailing structural system and strength of the structure is of prime important as defined in new code of the IRC. Now, just to understand the state of art design, just we take the example of the various pier. Now, why we are discussing pier? Because as we see, that superstructure is not going to contribute anything for the seismic resistance. It is only the pier at the bottom which will carry all the seismic force. So we should smartly select the section of the pier in a way that it perform very efficiently during the seismic. Now in sphere, we are having the circular section. Now circular section is considered to be the most efficient from seismic point of view. If the demand of the seismic resistance is more or less equal in both the direction, transverse and longitudinal. Right? At the same time, it's also provide the very effective confinement detailing. Also restrain the buckling of the bar during the effect of the lateral forces. Now, other option is to have the rectangular section if we are not okay with the circular section. But the problem with the rectangular section is that uh, basically there are very limited resources we are having, very limited detailing we are having to protect the main reinforcement bar from the buckling. Right? At the same time, the core of the core concrete of these structures remain unreinforced. If you see in the section DD, right, it is a rectangular pier. We can provide the stirrups on the outer perimeter, but the entire core concrete inside the concrete is unreinforced. Right? To improve it, we can adopt the section E, where the internally we can put the stirrups and links and all that. But basically, it is adding the cost to the structure. We have to use more reinforcement. Now, reinforcement is very congested in this area, so it is very difficult, or it requires extra efforts for the concreting. Right? And at the same time, this additional stirrups or reinforcement which we have provided is not required basically to take up the shear. Right? Shear strength might be okay with the stirrups which we are provided in the section DD itself. Right? So whatever the additional stirrups arrangement we have proposed in section E is just to have the core concrete confined itself. Right? So more or the less, we do not consider the rectangular section as a effective section in the seismic design point of view. And third is the section GG, right? Which is as I discussed, at wall type pier. One dimension is very high, very more compared to the other dimension. Stiffness of the column in this type of the shape is very different in each direction. So its behavior under the seismic in different direction is very unpredictable. Very rigid in one direction and very flexible in other direction. Okay. Now, with the limited options available for the shape of the pier, square, circular, and rectangular, there is other system also which we can adopt. It is a single column system or multi-column system. You can see the figure we have put down at the bottom of this slide. Let's we compare point by point the benefits and demerits of each of the system. When we propose the single column system, it is very easy to design and construct. Very easy to design in a way that it is a pure cantilever itself, right? You just have to do WL by 2 or WL square by 2. That's it, right? It is very easy. Single shape of the formwork you have to like, only vertical reinforcement, stirrups, and just you pour the concrete. Right? This is also very suitable if the uniform forces are acting on each direction in transverse or longitudinal direction. There is no issue with the behavior of this type of problem. More important is there is only plastic hinge will be at the one location. If it is a pure cantilever, it is at the bottom. Plastic hinge means where the more flexible stresses will concentrate. Right? So in the cantilever, it will be near the support. Right? So prediction of the behavior of this type of the pier is very clear to us. We do not have any doubt that the yielding will occur at any other point. It will definitely at the single location and at the bottom of the pier. But the problem is that it is a very determinant structure and hence having the very low redundancy. Right? Because of the cantilever shape, it requires the high demand at the base, and we have to consume more material at the base. Uh, yes, sir. Okay, I think we can continue. Uh, so, because of the high flexure demand at the base, we require the more material over there, and more material make this structure more rigid. Rigid structure is not advisable or preferable in the case of the seismic. Right? Uh, the last demerit of this is we cannot make the base of the pier as a hinge because there is only one support. It is a determinant structure. We have the detailing to sustain the moments at the same time. So we compulsory should have the fixed arrangement, fixed support arrangement at the base of the column, right? And because of the fixed arrangement at the base of the column, whatever the maximum forces we are extracting at the base of the column, all the forces are to be transformed to the foundation, and our foundation becomes very heavy because of this. Right? On the other hand, uh, for the multi-column system, uh, it gives the frame system, and we know that frame system is always better in any type of the structural system. Now, when frame system is there, uh, we are having the possibility of the distribution of the moments from one column to the other column. Right? So there might not be a concentration of the forces at one location, or even if there is a concentration of the forces in one of the column from this system, there is a chance of the redistribution of the moment before failure of the column. Right? So this is the most advantageous behavior of the frame system. On the other hand, in the demerits, response is more complicated. Right? We do not understand that how the system will behave under the lateral loading, because the yielding point or maximum moment is shear zone depends on many parameters. It depends on the spacing of the frame, the spacing of the column, size of the column, distance between two columns, height of the column. So many parameters are there. With the variation of each the parameter, the behavior of the system will be different. Right? So response is not that predictable as in the case of the single peer, right? Uh, Now, another point is that when we propose the frame system, we have to keep in mind that our detailing should be in a way that entire system works in a frame. Right? It means the detailing of the reinforcement from column to superstructure, column to foundation should be properly detailed so that each of the joint is capable to transfer the force from one to other. Now, talking about the response reduction factor, which we have seen in the previous slide, that recently code has taken care of the response of the structure. Just to give the emphasis on the effect of the system of the response factor. If you remember that in the alpha h equation, z by 2 I by r is in the denominator, right? So higher the value of the r, lesser will be the seismic force. Right? So our structural systems should be such that we are having the highest value of the possible response reduction factor. So if you see in this table is given in the IRC, and it is saying that different type of the structural system will have the different value of the response reduction factor. Right? So the designer is having the flexibility to choose the structural system in a way that it can have the highest R factor, and so that they are having the lowest value of the seismic force possible. So if we see over here, if we select the RCC voltaic pier, which in which the rectangular pier, where is the one dimension is very large compared to the other dimension, the response reduction factor is the lowest one, right? Because we cannot predict we cannot have the hinge in the transit direction because of the high rigidity of the structure in this direction. But on the other hand, if we go for the longitudinal or single pier, single column pier, we can have the response relation factor of the 3. So compared to the wall pier, we can have the 1/3 of the seismic force to design in our structure. Okay? So this is very important to understand and to keep in mind while we select the type of the supporting system in the bridge. Okay. So besides the state of art design which we have discussed, the code has put the more emphasis on the ductile detailing. Now, what is ductile detailing and how to take care? Just before that, just we understand that what are the problems are being faced in the past earthquake because of the inadequate ductile detailing or non ductile detailing. We basically found that the core concrete or cover concrete has been spoiled off, right? Reinforcement has buckled. Longitudinal reinforcement, which is the main force transferring element, has been buckled, and the core concrete has completely crushed. If you see in the second photograph, the complete core concrete has been crushed. Now, this is almost a damaged column, which cannot be repaired in any case, right? So these are this type of the severe damages we have observed in the past earthquake because of the improper or at all no ductile detailing. Second is a shear failure. Now, shear failure is that type of the failure which is many a time very difficult to control, because we know that to have the good resistance of the shear for any structure, we require the larger the depth, right? And larger the depth in seismic, structure makes more rigid. Structures having the larger depth, it will be more rigid. Structure is more rigid, it will attract more force. Right? So to tackle the shear failure in the pier itself is a very challenging, right? So we can say that that is only single parameter or very limited parameter to control the shear. The capacity of the structure cannot be controlled. We have to increasing the size to have the safe shear design, and increasing the size will attract the more seismic force. So it is a cyclic process. It is a circular loop. We are going to deep and deep into the problem. This has made the code to reform in two type of the system. One is based on the force base and second is based on the capacity. But before that, some relaxations has been given by the code that culverts and small bridges, minor bridges up to 10-meter length uh, in zone 2 and 3, the small bridges up to 60-meter length and span having 15-meter are not considered to be design. Now, whatever may be the criteria, now it is very important to understand why such relaxations are given. Right? If we try to understand those relaxations, we came to it can be very clear to in our mind that what philosophy has been developed by the code committee during the formation of the code. Right? That is that the code is not intended to have the foolproof seismic design. They do not want that your structure should be seismic proof. Right? The limited damage or damage of the selected member are acceptable, right? Because the damage to the particular single or some of the member is not completely collapse of the structures. On the other hand, if we intend to have the seismic proof design, the cost of the structure is so much that no one can expense us so much of the amount in a single structure. So the some of the unimportant structure having the small in the size, which can be easily repairable, are kept out of the scope of the design of the earth. Now, to meet with the shear and flexural design criteria, code has defined two different systems, which can be used for the analysis of the seismic. First seismic analysis method is elastic seismic acceleration method, ESAM method. Basically, this system is the very fundamental use of the response spectrum method, right, in which the fundamental part of the vibration only is to be used. All the seismic criteria, seismic coefficient we can use. We do not need to have the dynamic analysis in this job. For which type of the structure we can use this system, the elastic seismic acceleration system. So a very simple bridge which are having the skew not more than 30 degree, radius not more than 100 meter, and PR not more than 30 meter. We can design all the bridges under the ESAM method. Now, more systematic, sophisticated, and rigorous method is the elastic response spectrum method, which can be applied to the structure which are more complicated in the geometry, in the magnitude, and in the nature. Having the higher skew, large radius, PR height is very low, in which the fundamental mode of the response is not sufficient to predict the behavior of the structure, in which we have to carry out the dynamic response analysis, where first as well as all the subsequent mode has to be considered, and we have to find out that what are the higher modes which we need to consider during the design. Uh, Depending based on all these two methods, seismic analysis method and response method, the basic philosophy developed by the code is the strong beam weak column. Right? Strong beam weak column, entirely reverse from the building. Why here strong beam weak column theory is used? Because as we have seen in the formation of the geometry of the bridge, that the most vulnerable and highest force taking element in the system is pier, right? So pier should be designed as the weakest element so that the entire force can be covered at the one location itself. So while during designing the pier or bridge system, we should keep in our mind that it is okay if our pier or vertical member is observing some deficiency or damage during the earthquake. But our substructure, sorry, our superstructure and foundation should not fail or should not feel any damage. Right? So this is the philosophy of the strong beam and weak column. Now to safeguard this foundation below the ground level, as per this philosophy, a code has given the overstrength factor, right? Because as we seen that the pier is fixedly connected with the foundations. There is no other way that the force from the pier can be reduced for the structure and foundations. It means whatever the force will be at the base of the pier, the same amount of the force will be at the foundation. In this case, in this scenario, how to safeguard the foundation? And for that, code has proposed the overstrength factor to be applied to the bridge foundation in the design. Now, the purpose of the overstrength foundation is not just to increase the capacity of the foundation compared to the pier, but it has several other aspects also in the consideration. One is the unintentional increase in the material properties. Whatever the material properties we have considered in the design, might be possible that those are the okay. There is one question that why strong beam weak column concept has been given over here. So because here most of the time if we see that our superstructure or the beam element, horizontal element is just simply supported on the column, on the pier, right? So it means that superstructure itself is not contributing anything to the seismic resistance. It is just acting as a lump mass, right? And on the other hand, column is the element which is experiencing the highest stresses during the earthquake. Right? So if we consider the weak column, it means by considering a weak column, what we are doing, we are not designing the column weak, but we are considering that this element, this column element is the weakest point. So we are giving the more concentration on the design of this, right? So that's why we are considering the column as a weak, and we are giving the more concentration to the column while designing for the seismic forces. Right? On the second case, suppose our structure is a integral one, in which the superstructure is also having the beam which is going to contribute in the seismic resistance or seismic behavior. In that case, what will happen if we consider the big beam theory? It means we are allowing to formate the hinge or some local damage to the superstructure itself. Right now, the repairing of the superstructure itself is a very challenging and address to the very other aspect, because superstructure many a time it is composed of the bearing cords, other furniture elements like crash barrier, footpath, railing, parapet, and all that. Right? In presence of all these, to repair the superstructure from all the around, all the perimeter, it is bit difficult compared to the repair of the column. Repair of the column is also very easy because it is at the ground level. No particular staging or supporting arrangement is required to carry out the repair. Very accessible to inspect and all that. Hence, strong beam with column theory has been adopted in the philosophy of the I think uh, it is okay. It is understandable. Okay. Now, overstrain factor. Now, just we try to understand what is overstrain factor. Basically, overstrain factor is the magnification factor given to the capacity of the structure. Right? Now, what is the capacity of the structure and what is the demand of the structure? In case of the pier and foundation, demand of the foundation is that pier will transfer its full force to the foundation. Now, if we design the foundation for the demand only, it is more likely that foundation may also having the same intensity of the stress, it may experience the damage. But our intention is that foundation should not have any damage. It means we should have the higher capacity of the foundation than its demand, compared to its demand. So the factor of the capacity to the demand is the overstrength factor. And in the IRC SP14, 35% of the increase is given to the concrete substructure and 25% is given to the 1.25. Yes. I think somebody is raising the hand. I'm not sure how I can respond to you.
Actually, sir, we have told them that they should place their question in QA box and we will
correct.
answer accordingly.
That will be
Sometimes
fine.
sometimes by mistake
They may have,
that happens.
yes,
Yeah.
yes, right. So it will be okay. At the end of the session, we can discuss all the questions. When we can
Yeah, sure.
go back to the slides also if required. It will not.
Yeah, sure.
Yes. Thank you. Okay, so 35% increment in the forces is given to the foundation in the case of the concrete structures and 25% to the steel structures. Now, depending on the new provisions of the code, the new code is completely following the philosophy of the capacity based design. Yeah. Now, to understand the capacity of based design, let's we first understand what was the philosophy was sorry, what the philosophy was prevailing before the SP114. So earlier the force-based design was followed in all of the codes, not even in the India, all over the world. Force-based design was given. In the force-based design, basically what we are doing, we are just analyzing the structure for the seismic, finding out the various stress requirement. Based on the stress requirement, we fix up the sizes and amount of the reinforcement for the structure. And to safeguard the structure, we just limit the permissible stresses. Right? So we are only having one tool to safeguard the structure is to limit the permissible limit. of the actual material stresses. So every time with the increased intensity of the seismic force, we are increasing the force on the structures. Okay? So this is called the force-based design. Right? While adopting the force-based design, the structure always uses the elastic model, right, to predict its strength. It never overcome or never cross the elastic model and never allowed to go into the plastic model. Okay? So this was the force-based design. Now problem with the force-based design was that as the higher the seismic zone, higher the seismic demand, the structure becomes more stiff because higher the seismic demand, higher the force is there, and we require the more material to withstand this force, and more material in a way attracting the more rigidity. So it was somehow felt that this is not a proper solution. That every time we are increasing the material and making the structure strong from the force point of view, but we are making the structure weak from flexibility point of view. Basically, more the flexible is the structure, more the good behavior in the seismic is there. Yeah. So this was the force-based design. Now, on the other hand, in the recent design approach of the capacity design, it was given the importance to the state-of-art design, which we have discussed. That we should consider the proper selection of the member, which is more flexible, which allows the more energy dissipation. Right? More energy dissipation means it will allow the good behavior during the earthquake. It will yield late, or even after yielding, it has the chance to enter into the plastic zone. Now, when the structure enter in the plastic zone, it is now vulnerable for the collapse. In that zone, the ductility has come into the picture. Right? So, in capacity-based design, ductility criteria is given the prime importance, but at the same time, it was emphasized that ductility should be given in the bending action only. It means we should make our concrete confined in a way that ductility is available for the flexural action only, not in the shear and axial action. Right? Because both shear and axial behavior of the concrete is a brittle behavior. So it means we should not compromise on the shear and axial capacity of the concrete. Rather, we should make more ductility in the flexural action. So by this, we are allowing the structure to yield more in the flexural. Right? By this, we ensure that during any seismic event, our structure will reach to its capacity first in the flexural, not in shear. Because if the shear capacity is achieved first, it will lead to the brittle failure or sudden failure of the structure. It will not give the damage, just a small damage, but it will give the complete collapse of the structure without any warning. Now, this concept is the capacity design. Means, so broadly, if you want to say, we can say that capacity design is that we are not assuming the amount of the seismic force. We are assuming the capacity of the design. Now, whatever the capacity of the design, we intend our structure to design for this force for the seismic and allow the structure to enter into the plastic zone. In a bridge pier, at the junction of pier and pile, we generally prefer to have the yielding at the particular this location, because this is the bottommost part of the structure, very near to the ground, easily accessible, and can be easily repaired also. By doing this capacity design and yielding at the bottom of the pier, we are ensuring that no force will transfer to the foundation. Now, the beauty of the capacity design and allowing the yielding of the bending first prior to the shear is that once the pier is yield in the flexure, no further stresses will transfer to the foundation. So automatically we have set by the foundation for the transfer or sustain of the higher forces. Now, To understand more deeply the shear capacity or capacity demand, we have to understand that how structure should behave under the seismic. Now, for any ductile failure model, we require that structure under the lateral forces should undergo large deformation, right? Because higher the deformation, more the energy dissipation. In seismic, energy dissipation is very supportive parameter to sustain the seismic force in our structures. Okay. So large deformation and energy dissipation can be allowed because of the ductile failure model of the flexure only. This is not possible for the brittle failure model of the shear. That's why also we have given the importance of the flexural model in the ductile behavior. Now, to have further more clarification on the ductile and brittle behavior, we have taken the example of a chain. Right? One chain is made up of different link. Each link is having the different capacity. Right? So if you pull this chain from both the end, and if you want that particular any one element should break first, right? So what we require? We require to make it ductile. Right? And why we require that particular element to break first? Because we know that that particular element, the red element in this slide, is a ductile element. And ductile element will give us the warning before the failure. It means the failure of this link will not be sudden. So we will have beforehand warning that this structure is going to break from one end. Okay. So because the link which is the brittle in nature, having the higher capacity, it will not break fast, but the ductile link will break fast. So we are having the sufficient warning before failure of the structure, and we can take the precautionary actions to that. Now, to have the selection of the plastic hinge, the code has given the various pictures, which is very logical. Right? To determine the plastic hinge, the very simple principle is to we adopt is that what is the highest flexure zone? What is the point? Where is the highest flexure moment we are experiencing? That is the plastic hinge. In the cantilever pier, naturally it is at the bottom of the pier. Right? In case of the pile foundation, when we adopt a pile foundation and it is rigidly connected with the pile cap, it is fixed at top and at bottom also. At bottom, when we said bottom, it does not mean the termination of the pile, but at the fixity point of the pile. So pile is having the two hinge point and pier is having the one hinge point. In the frame type system, means the pier is made up of two columns. We are having two different locations where the hinge can be at top and at bottom also, similarly at the pile. Now, if you see in the pile, there are very defined location of the hinge. But suppose we have adopted the hinge in the pile, you just imagine how we can come to know that there is a damage during the earthquake, because it is completely buried in the soil. Right? And also it is very difficult to repair these hinges also, damage to the hinge also. Right? That's why the overstring factor of 35% is given to the foundation. That the capacity of the foundation should be 35% more than capacity of the hinge at the B. So that under the seismic condition, the hinge will form first in the pier. Right? It will fail, so the second hill will not develop in the pipe. Now this is very interesting. Right? This is the example of the plate type pier or wall type pier which we have discussed, in which the one dimension of the column is very small compared to the other dimension. So in the left hand side figure, if you see, the thickness of the pier is very limited. So in this direction, when the seismic force is acting to right angle to it, it can easily form a hinge. Right? It is a very flexible in this point. So it can, but on the other dimension, in the transverse direction, the dimension is very wide. Right? Dimension is very wide. So now to have the hinge in this direction is not possible because it is very rigid. It cannot be yield. Right? So the same type of the system, in the same type of the system, we can provide the ductility in one direction only. We cannot provide the ductility in transverse directions. Okay. So as far as possible, we should try to avoid such type of the selection of the member, which is having the difference of the ductility in either directions. Or in the simple way, if you want to say, we should try to avoid the such member size of the pier in which the flexibility in different direction is very vast. Right? Difference between the flexibility is very, this is very rigid in the transverse direction. So it will attract more force. Right? So though we have safeguard our structure in this direction, but it is very vulnerable in transverse direction. So even in the design calculation, if you put the figures to the calculation, we found that we require the higher forces for this pier and we require the very heavy foundation for this type of the pier compared to the circular or square pier. Now coming to the detailing part, basically in all type of the structure, not for the seismic also, for other type of the load, whatever may be the figures saying during the calculation, whatever the detailing we are following, that is more important. And while we say the detailing is just, it does not mean just the numbers. It means 32 dia 10 numbers reinforcement is not just detailing, right? Detailing means how we are providing the reinforcement. What is the location? What is the anchorage? What is the development length? What is the core concrete embedment we are proposing? That all has itself is a very important role. Those calculations are not reflecting in our calculation, right? But it is very much important, and most importantly in seismic, while we consider that structure should be ductile, the detailing is very much important, right? Now to understand the behavior of the concrete under ductility, basically we know that concrete itself by its own nature, it is a very brittle material and it suddenly fails, right? And we never intend to have our structure of the such type that it fails before burning, right? But concrete also can be made ductile with the proper confining reinforcement. Concrete, if concrete is confined all around from the reinforcement, then brittle failure or bulging or collapse of the structure will not occur. Right? It means that confinement is not just increasing the strength of the concrete. Definitely, it increases the strength of the concrete. If you are aware of the IS 456 provision, it is given in the column clause that properly confined concrete with the stirrups, we can consider the 5% higher strength in the compressive stresses. Right? So, means definitely with the confinement, concrete increases its strength, but also tremendously it increases the ductility of the concrete also. Right? Now, more ductile is the concrete, more allowable displacement and more energy dissipation. And the structure having more energy dissipation, it is having a very good performance during the system. Right? Now, confinement basically in the concrete can be achieved by the stirrups, various shape of the stirrups based on the shape of our concrete. But most important is that any stirrups which we provide to confine the concrete should hook inside the core concrete at 135 degrees. This is a very important code later on the code is there. Because suppose you have provided a sufficient number of the stirrups for the confinement of the concrete and those stirrups are not properly secured in the core concrete, what will happen during the lateral force? During the lateral force, the hoop stresses in the concrete itself will develop, right? And those hoop stresses will try to open up the stirrups. And once the stirrups is open up, complete confinement of the concrete is lost and concrete will brittle away. So it is very much necessary, it is very much required that any confinement stirrups we propose should be projecting into the core concrete. Now, just I would like to discuss about the most dangerous and most seen failure of the bridge, which is the displacement of the structures. I just want to discuss various incidents and how to take care in the detailing of the bridge, how we are taking and what the code is providing for the provisions. Basically, the superstructure is supported on the substructure with the element of the bearing, and these bearing are very small in size compared to all other elements of the bridge, and having the nature of fragile and brittle. Uh, Basically, the capacity of the bearing is quite high to take up the vertical loads or gravity loads, but is having the very limited capacity to take up the lateral forces. In general, the capacity of the resistance of the lateral force is almost about 25 to 30% of the vertical load. Right? It means whatever the vertical load acting on the bearing, 25% of the seismic force produced in the lateral direction can be taken by this place. If the force is more than this percentage, the bearing will not respond properly or not perform properly. Right? And under the poor performance of the bearing or failure of the bearing, large displacement of the superstructure will occur, and sometimes is called the complete collapse of the superstructure from the bearing itself. Now to safeguard it, first and very fundamental rule the code has given is that one should propose proper seating length of the structure into the pier and abutment. Because it is just we have put rested on the structure on the bearing, we should have the sufficient width of the seating over the bearing so that it will allow some displacement and will not cause the complete collapse of the structure. Now, many a time, just the seating length of the structure at the support is not sufficient because in the higher seismic zone of 4 and 5, the distance of the superstructure amount of the displacement is so high that even with the sufficient seating length, structure may dislodge from its position. Right? For that, a seismic arrestor or reaction blocks are proposed by the code. Now, these seismic arresters are the concrete projected from the pier cap and superstructure and in contact with each other, so that if there is a lateral movement of the structure is there, if you see over here, I have pointed out the arrow, right? Some concrete is projected from the pier cap. So if the structure is uh, try to dislodge from its position, this concrete projection will protect it. Right? So this is the seismic arrestor or reaction blocks. Now there are very wide range of the provisions of this clause. Many varieties we can provide. One of them is we can project one reaction block from the end beam of the superstructure itself, and the pedestal can arrested by this seismic arrestor. In the below figure, we can have the one single concrete element protruding from the pier cap and arrested by the two girder system. If it is a box type structure, we can have the opening in between at the support section of the box and can protrude one seismic arrestor concrete element from the pier cap. So by this, we can ensure that during the lateral forces, the structures will remain in its position and bearing will not have to take care of these additional lateral forces. If we design the bearing just for the vertical load, it is sufficient. Now, one detailing issues we are facing while providing the seismic arrestor or reaction block is there. That whatever the concrete element we are projecting from the pier cap and whatever the part of the superstructure we are considering to arrest the movement, both are the concrete. Right? If you put both the concrete side by side during the lateral movement or during the lateral shock of the earthquake, this concrete may crush because both the concrete are touching to each other with some impact loading. So there is a provision to provide a small elastomeric pad. Some rubber pad should be there in between. It means between the structural element of the superstructure and structural element of the tension block. Some element should be put over there. It is a rubber which will act as a buffer, right? So it has dual purpose. It will also not allow the concrete of superstructure of radiation blocks to crush. At the same time, it will also act as a dumping. Whatever the impact load or transfer from the superstructure will give some damping effect before transferring to the radiation block, and by this transferring to the field, right? So this is one of the very good detailing practice which what is also recommended and we should follow while proposing the seismic arrest of the superstructures. So I think I have covered most of the parameters and written recent practice which are following the seismic design of the bridge. Just to give the end notes, um, as per the latest seismic provisions of the IRC code, more emphasis is given on the structural configuration, state of art method, rather than magnifying the force. To design for the higher force is now not of the important or not, or we can say to design for the higher force is now not in the fashion, right? Now the trend is to develop the system or propose the system in a way which is more friendly in the seismic events, right? Some of the examples of such system are: one is the integral bridges in which superstructure is properly connected with the substructure, which is not having the bearing. So transfer of the force is very good over here. So we are having designer is having a very good chance or vast field to demonstrate the seismic force behavior and detailing point of view all the time. As far as possible, we should try to avoid the skew and curvature bridges. That as far as possible, because sometimes the geometry or location of the structure cannot allow all the freedom. But as far as possible, we should contribute more to the length of the bridge. We should add more to the length of the bridge, but try to avoid the curvature and high skew. Because of the curvature and high skew of the bridge, during the seismic event, the structure really behave very strangely. Right? And the most difficult and most dangerous is that the torsion mode of the structure. Right? I think you must all will be aware of the torsion mode in the building. But to control the torsion mode in the building is very easy because it is a very wide base frame structures. Right? So there are very many ways in the building to control the torsion mode to provide the shear keys at various locations in the various magnitude. But in the bridge, we are having only three elements: superstructure, substructure, and foundations. So once our bridge structure is fall into the torsion mode, it is very difficult to control. Right? And skew and curvature of the bridge is very prone to have the torsion mode. Thirdly, continuous bridge. Continuous bridge means having the expansion joint at every pier location. We should try to adopt the practice of the continuous bridge. The expansion joint is having the saddle support. Right? In this case, the 2, 3, or 5 force spans can act together. So dislodgement of the structure basically can be controlled to the large extent. Fourth and very important parameter, that is the vital superstructures. We should try to configure our carriageway. We should try to configure our span in such a way that superstructure is not heavy. Because as we have discussed today, that superstructure is just acting as a lump mass over the cantilever pier. Now, if this lump mass is very high, it will attract the more force, and our substructures and foundation will be very heavy. So, while prepare the geometry of the bridge itself, we should try to keep in mind that we should propose such type of the arrangement that superstructure is having the minimum weight. Now, some of the issues we are facing at all the time, basically in case of the seismic, that we are experiencing that Codal revisions are too different, too frequent. Right? Every year in the bridge, it is now a scenario that every year or sometimes every 6 months we are getting the new provisions of the system. So sometimes it is happened that while we are designing, we are having one set of the clauses to be adopted in the design. While during the construction after 6 months, the entire the system is changed. So we are always remain in the doubt that whether we should redesign with the new clauses or whatever the clauses are given is okay. So it is a challenge that right now we are, but at the same time it is required also to overcome this problem. It should not be that we should stop the quarter provisions. It is required also to cope up with all the sudden, all the recent development of the science and practical knowledge of the theory. Uh, at the same time, the second problem is the inconsistency between the different codes. Uh, Basically, for the bridge, there are two codes. One code is given by the IRC. IRC has given IRC SP 56, IRC 14 for the seismic design. At the same time, Indian standard is also given IS 1893 Part 3 for the bridges. Now, sometimes it seems surprising that when in our country the design is not allowed as per the IS code, why the clauses should be laid down for the seismic design of the bridge in the IS? Right? And sometimes we are really face very much struggle during the approval of our design also, when some persons also point out for the seismic provisions of the IS code. And it is very difficult because both the fundamentals are having the different bases and different philosophy to adopt. Last point that uh, just to have the recent developed code with us is not just important. It is also equally important for all of us, means practicing engineer as well as all the students who are um, in the academics of the civil engineering. That they should aware of the codes. They should aware of the codes, and to be aware of the code is a one thing, and to understand the code is a different thing. Once we say that now the recent code is saying that we should follow the capacity design. Okay, if we accept that capacity design is to be adopted and we follow the 1, 2, 3, 4, 5 clause, our work will be done. But whether we have developed the understanding, what is the capacity design, what was the force-based design. Now capacity design is more preferable than force-based design. This is, I think, for me, as per my understanding, this is more important to have the proper understanding of each code and each clause. We should also aware of the science behind that. Why this clause has been changed, why this clause is adopted. The basic engineering we should also aware, so that only we can be sensitive to that clause. But unless and otherwise we do not understand of the importance of those clause, we cannot be sensitive to that clause. Sometimes it may happen that we overlook it, right? And for that, it is necessary that we should have more and more workshop on this. We should have more workshop on the theory of the course. We should have more workshop on the basic science of the course. We should have more elaborated explanatory notes of the course. And it is also necessary that all the workshop and necessary explanatory notes should be come immediately after release of the code. Many times we have observed that explanatory or workshop are after 10 years of the release of the code. So now almost we can say that up to the 10 years, most of the people have followed the practice works as per their own understanding goals. They have not gone or they have not penetrated into the theme of the code committee or theme of the complete engineering thought behind the revision of those. I am closing my discussion with this photograph. This photograph is one of my favorite photographs in context of the bridge design. This photograph is taken by me in 2002, just after the Bhuj earthquake. 30 kilometers from the epicenter of the Bhuj, in the one somewhere in the river. Frankly speaking, I have first time seen such type of the pier. All the time what we have seen is the pier of the solid, circular, square, rectangle, wall type and all that. The building type system has been followed over here. If you see 4 columns, tied at various intervals with each other. Columns are made vertically slant, having the wide base, small top at the location of the superstructure. And surprisingly, this bridge has observed no damage at all. When we have found out that how old is this bridge was constructed in 74, right? Where the seismic coefficient method was in implications. Right? Was the force-based design in which the flexibility of the system was not in come into the picture in the seismic design itself. Even though the structure designed during that phase has withstood the highest seismic in design. Right? So what I mean to say is that whatever the science, whatever the engineering, whatever the whatever provisions given by that, it has its own important. It has its own taste, right? But what judgment as an engineer, what structural system as an engineer we can develop, no one can defeat it, right? Even the highest earthquake can be withstood if we have developed a proper system of our structures. So I would like to thank all for your patience and uh,
So, so thank you, sir, for very nice presentation. Uh, so we'll take the few questions as we have in the question box.
so,
Yeah. So what will be the main difference between earthquake analysis of bridge and normal buildings?
so main difference is that in the building, uh, if we see the geometry wise, the building all the time is the frame structures. Okay? So the building is having the more supports scattered around the structures. It is connected with the all the diaphragm actions of the slab and them, which is not present in the bridge. More or less, bridge cantilever structures. Right? Secondly, the response reduction factor. Right? In the building, there are two response reduction factor values been given. One is 4, R equal to 4 and R equal to 5. Ordinary frame system and special resistance system. Okay. But same is not in the case of the bridge. The highest response factor given is 3 only. Right? That is again because due to the case that the format of the bridge is entirely different from the building. The more or less time it is determinant structures. So transfer of the force from one element to other element is not allowable, not possible in the bridge.
So fundamentally, the type of structures, they are different. So
Different.
accordingly, yeah.
Yes.
So accordingly, their analysis will be different.
And yes, and most of the time we have to go into the dynamic analysis in the building, but it is not necessary all the time for the bridges of the small span and small height. It is not required. First mode, fundamental mode itself is the sufficient for the bridge.
Right. The next question is the seismic behavior of balanced cantilever bridge is the same as simply supported bridge or not? So
Yeah, it is entirely different.
yes.
Entirely different, and many a time, in the case of the balanced cantilever method, sometimes the construction stage earthquake is more dominant than the service stage earthquake. Though the code has given the relaxation in the magnitude of the seismic during the construction stage, right? So second part is that in the balanced cantilever bridge, moreover, it is connected with the pier. Connected with the pier. Just I will draw one sketch over here. This is the pier, right? And let's say this is the arm of the balance cantilever. Arm of the balance cantilever. Now, whatever the seismic force acting are transferring to the pier. Now, as this is a balance cantilever, all the time it will behave as a cantilever, right? So any out of plane force acting on this will create the torsion in PR, right? So it is more critical in the design of the pier to design for the torsional forces. Generally not there in the simply supported. Mostly the simply supported bridge, the superstructure construction is done in a way that torsional stresses are not there. Directional flexural moment only.
Yes.
Right. So if we observe the supports of the ballast cantilever bridge, you just always to try to see it is as the wide base at the bottom. Right. Many a time it is a hollow. So more perimeter can be given, and more perimeter is very supporting to the torsional resistance.
Torsional, yes.
Yes.
So next question is, how do you clear the torsional mode in bridges?
Right. Generally, most of the time, we try to avoid the torsional mode from the geometry setup only. We try to put up the geometry of the structure in a way that there is no torsion mode. But suppose in the case of the balance cantilever or a very high pier, which is having the different stiffness, we try to give the frame type structures, right? In which different column system, instead of a single column we define, right? Tie with the one, and sometimes if this is not sufficient, we give the diaphragm wall in between. Like right? This diaphragm wall is very having the resistance for the torsion in there. Basically, whatever the shear walls we are adopting in the building, we are just trying to put the same principle over here. But the problem is there, we are having very limited space to put the diaphragm wall.
Right. Okay. So next is, what about the variation of BM with skew angle? It is increasing or decreasing?
Right. It is actually it is increasing also. It is decreasing also. Right.
Yeah.
If we see the geometry of the skew, it is basically suppose in plan this is a square. In geometry we are having like this. So in plan if we see, it is developing two angles. One is the acute angle and one is the obtuse angle. This is the acute angle and this is the obtuse angle, right? Acute angle, obtuse angle is having the more concrete, so more force concentration will be over here. And acute angle is having the less concrete, so less force concentration will be here. So the force will be concentrated over here. So here will be the force will be more, and here force will be less. Right. So the distribution will be different. It will not be uniform in this. At the same time, the second problem is that though at the acute angle, force concentration is small, but there is a concrete area is also small. So if you put a point load over here, this concrete will bend upward. Right? This is not allowed. So in that case, what we do, we put an end beam over here, right, projecting beyond the deck, and this deck is entirely connected with this end beam. That this beam, which is connected with slab, will not allow to deflect the slab in reverse direction.
Right. So then next question, in load calculation, should the wearing cot load be a permanent load or temporary load?
Yes, basically wearing load is a permanent load, but in the IRC, the wearing cot is given the highest load factor. Basically, the IRC limit state is being followed right now. Right? So different load factor is given, but wearing is given the factor of 1.75. Whatever the wearing cot load is that we have to increase by 75%. Other load factor is 35%. Now this is because the wearing cot is the surface which will suffer the wear and tear day and day. So there are the chances that overlay of the varying cord will be there in future. So increased load will be there.
Yeah.
But at the same time, it is the permanent load only.
Hmm. So I think it is answered.
Yeah.
The participant is again asking that it is a temporary load or permanent load. So it
No,
is a
it is
permanent load only.
permanent load. Actually, in the bridge, if you have say in detail, in the bridge there is no temporary load. There
Yeah.
are two type of the load. One is the permanent load, and one is the
Hmm.
variable load.
Hmm.
The variable load, that is the vehicular movement.
Hmm.
Whatever the vehicular movement, it may happen the occurrence of the vehicle or presence of the vehicle at instance. At the second, it may not be there.
Hmm.
At the same time, wind force
Hmm.
is a variable load. Seismic force is
Hmm.
a variable load.
Hmm.
So it is different as a permanent load and variable load.
The next is, what is your recommendation in multi-span bridges, whether to go for continuous bridge or simply supported bridge?
Basically, we should go for the continuous bridge, right? Because with the continuity of the several span, we are also getting the good performance against the span dislodge. At the same time, we are getting the other benefit also. In the continuous span, we are having the very few expansion joints.
Hmm.
While we say a continuous span, it means here there will be the expansion joint is not there, right? And expansion joint is not there. It means we will get the good riding surface. I think all of us has experience. And when we pass from the bridge at the expansion joint location, we feel some shocks or jerks, right? It is because of the expansion joint itself.
Hmm.
Right? So it is always preferable to have the continuous span.
Hmm.
And nowadays continuity can be achieved from the reinforcement also and weak spacing also.
Hmm.
Now it is very sophisticated and good tools are available for to have the continuity.
Hmm.
And most of the time in the major city of the India,
Hmm.
the urban flyovers, it is a there is a clause that the expansion joint should not be closer than minimum 100 meter.
Hmm. Right. And then last question, I think. The IRC code gives the load combination in terms of live load, relieved, etc. Can you elaborate on this?
Okay, so actually, IRC 6 is having the different tables for stability, for structural design, for SLS, and all that. So they have given the various definition of the load. One is the relief load, and one is the adding load. Right? Suppose I take an example of a cantilever structures over here. Right? So any load I put over here, will add to the bending moment.
Hmm.
Right? So if this load is P, right? Suppose this load is P, and if I have to apply the load factor to this, so if it is a real, if it is a adding load, it means it is adding the severity of the effect. I should give the highest factor.
Hmm.
Right? But on the other hand, if the structure is like that, let's say the simply separate structures. Sorry. In continuous structures like this. If I put a load over here, this is adding to this location, right? But
Hmm.
it's leaving the span moment over here.
Hmm.
Right? So if we intend to design this span moment, the load factor to this load should be given differently. So if you see in the table, the relieving load is given the minimum factor and the adding load is given the maximum factor.
Hmm.
It means while considering the relieving action, we should consider the lowest minimum, and while adding, we should consider the highest possible.
Hmm. You should think for the worst load combination.
First load combination. It
Yes.
should not happen that by applying
Hmm.
the load factor, we are
Hmm.
releasing the structures. We are
Hmm.
releasing the effect. It should not happen.
Yes.
like that.
Mhm.
And for the live load, I'm not sure whether he intended for this question only.
Mm.
There are other parameter also, leading load and accompanying load.
Mm.
Leading and accompanying. Uh, See, there are three variable loads: live load, seismic, and wind. So we should not predict that all three events in extremity will occur at the same time.
Mm.
It means that highest live load is passing the bridge and severe earthquake will come
Mm.
or severe cyclone will come.
Mm.
We should consider that earthquake is higher, live load is minimum,
Mm.
or live load is maximum, earthquake is minimum. So the factor of the accompanying leading is differently given in this code also.
Mm. Okay. And which is the most reliable software that you suggest
Uh,
in the bridge analysis?
for the fresh engineers and to students, I will not recommend any software. uh,
Okay.
Basically, because in the recent age of the computer,
Mm.
uh, I'm observing and sometimes feel for myself also that we have lost the touch of the basic understanding or fundamentals. We just
Mm.
the software.
Mm.
And software, any sophisticated software is just a tool for the engineer.
Mm.
So garbage in, garbage out.
Yes.
Unless and otherwise we do not understand the behavior of the structure, or we cannot predict the behavior of the structures, we cannot ensure that what data we have feed into the software it is correct or not. Right? But again, versatile software is dead.
Mm.
Can solve 90% of your problems in the basics design.
Mm.
But if you want to have some complicated structures, just like cantilever, in balance cantilever, actually we have to carry out the time analysis
Mm.
because different segments are erected at different time. So creep behavior of each segment will be different,
Mm.
and that is I accept that it is not possible with the manual calculation. So
Mm.
to feed the data. For that, Midas is good software. It
Yeah.
for user friendly.
Mm.
But broadly, if I would say that Sophistic is a software which is not very much popular in India. Is
Mm.
only few consultants. This is really versatile software,
Mm.
really versatile. So it actually carry out the perfect analysis, give the perfect understanding to us also, and the interface is very simple. So
Mm.
the chances of mistake by feeding the data is very less.
Right.
So Sophistic, I will recommend that it is the best software.
Okay. And one more question has come,
Yes.
that which code gives the load parameters of wearing code, railing, etc. Standard load value.
Right. Actually, IRC6 is the code for bridge having the title of load and species.
Mm.
So IRC6 gives all the details about the structural load, live load, wearing code, everything. But at the same time, to understand the geometry or structure of the all these parameters, we have to read the IRC5 also.
Mm.
IRC5 is basically general features of the bridge.
Mm.
Suggest that what should be the minimum thickness of the wearing cord, what type of the material we should use for the wearing cord, what should be the height of the footpath, what should be
Mm.
the width of the footpath, like that. So proper understanding can be developed for the load with the combination of IRC5 and IRC6.
Right.
And also somebody want to understand the bridge, sequence wise he should start with IRC5, 6, 112, like that.
Okay. And along with this, my question then, which is the
So
best book for the freshers to start with? Um,
it is a very tricky question. uh, I will say that best book for the bridge
uh,
in Indian scenario,
mm,
it is yet to come.
yeah. Mhm.
Till date, it is not. It means not means of the theoretical background.
Mm.
There are many books which are good. One is
Mm.
the book from the Rajagopalan sir,
Mm.
Rajagopalan sir, and Swami Saran books.
Ah.
They are fairly good.
Mm-hmm.
Every fresh engineer or startup can use. But the problem with each week, which is also good from the theoretical point, the problem we are facing is that there is a large gap between the theoretical analysis, theoretical and practical approach.
Yes.
What we are using in our design field,
Mm.
industry, it is very different from the whatever is written in the book.
Mm.
Or we can say that we can get only basic understanding from that book only.
Mm.
For have the practical understanding, we have to attend office only. And this is really pathetic situation
Mm.
for us, that after doing the 4 year of the bachelor's, 2 years of the master course, industry is saying us as a fresher.
Yes.
It is really pathetic. 6 year of the life in engineering and still
Mm.
facing this. The same case is not with the MBBS doctor.
Yeah.
So there is a gap somewhere, something.
Mm.
But Rajagopalan and Swami Saran book is really good.
Right. So I think, sir, we have answered all the questions in the box, and even we have got the appreciation in the box also, that you have explained each and everything very nicely, and top to bottom of the bridge analysis has been covered in the session. So on the behalf of Marwadi Education Foundation and Atal Academy, I'm very much thankful to you for sparing the time for this knowledge sharing session. And still, if we have some more doubts from the participants, we'll communicate to you and we'll try to solve their doubts.
Yes, yes. I will
Yeah,
reply through mail also, sir.
yeah,
And I also thank you to you and Marwadi University for giving me this opportunity to interact with all you people.
yeah.
Because my personal experience within last week, I have read a lot of material and
Hmm.
also get the new clarification in my mind, which I was understanding from the seismic point of view.
Yeah,
So it had added to my knowledge also.
yeah. So thank you again,
Yes, sir.
sir.
Okay.
Yeah, okay. So all the participants for the third day tomorrow will be joining again at 9:30. Okay. So with this, we end this session. Thank you one and all. Thank you, sir.